Hi, everybody. So we've been talking about lenses and how we can use that to focus light, to gather light, to increase the energy of the light that's coming in so that we can see things that we wouldn't have been able to see before because it was too faint. We also talk about how we can use that to magnify things or in some cases even reduce things. But lenses aren't the only way that we can do that. Mirrors are an extremely effective way to do basically the same thing. It's just instead of using the law of refraction, they're going to use the law of reflection. So we're going to talk about how we can apply mirrors to the same exact tasks that we've been doing with lenses. And you're going to see that they're very similar in a lot of ways. But mirrors and lenses both have advantages and disadvantages. And so we're going to try to cover which you would want to use in a different situation. All right, let's get started. Okay, so lenses have a number of disadvantages. Some of them may not be immediately obvious. We've talked about how a lens works by the fact that the index of refraction of the glass is higher than the index of refraction of air. So I get a light ray that comes in, it strikes the surface, and then it gets bent because of that higher index of refraction. It's going to get bent towards the normal. What we didn't talk about was the fact that the index of refraction of the material depends very slightly on the wavelength of the material. So if I have a white light coming in like this, the red light is going to get bent differently from the blue light. And so they'll be at slightly different angles. And then of course I'll have all the other ones in, all the other colors in here. Same thing here. So what that's going to mean then is that I'll have my image, my star or whatever, but then I'm going to have this kind of faint rainbow halo around it. And the most obvious thing I'm sure you've seen before is a prism. So if I've got white light coming in like this, the red and blue lights are going to get diffracted or refracted by a different amount. And then the other color is going to be in here. And then, of course, you get Pink Floyd's Dark Side of the Moon. But that's what's leading to giving you the rainbow. And this is how a rainbow in the sky works as well. You've got water droplets up in the air. When the sunlight comes in, it hits the back of that water droplet, and then it gets diffracted by different amounts, or refracted by different amounts as it reflects off the back of that water droplet. This is why the rainbow will always be found opposite the sun. So if the sun's on this side, the rainbow is going to be on this side because it's reflecting off the back. You see different colors because if I'm standing here, from this water droplet, I only see this ray. The rest of them are going over my head. And remember, if it doesn't go into my eye, I don't see it. However, from a water droplet down here, now maybe I'm seeing this color from here, and these are actually going into the ground where I missed them. So that's what's causing that stacking of colors. You're only seeing one color being refracted from that one particular water droplet. Well, if you're wanting to do science and you're trying to learn about stars or something like that, that's probably not a good thing. So this idea of this color error is called chromatic aberration. So we can fix that by using a mirror. And here I've got a spherical mirror. And just like with our spherical lenses, you imagine that you had this sphere of glass, and then we're just going to cut one piece out of it. And I don't have to cut it exactly in half. It doesn't matter. As long as it's part of that sphere there, then we're going to consider that to be a spherical mirror. Just like that. Well, this mirror is going to obey the law of reflection, which we've studied before. So how are these light rays going to move? How are they going to get reflected off of this surface? Remember, this is now a mirror. It's not a lens. Well, what does the law of reflection say? Well, it's very simple. It just says that the incident angle is equal to the reflected angle. And here, theta r is our reflected instead of our refracted angle. But remember that those are measured from the normal. So this would be the normal to my surface here. So it's going to get reflected out something like that. This one is coming in normal, so it actually comes straight back. If I can get that to draw. And then this one, here's my normal, something like that. And so it comes through here. And you see that all of that light gets focused right here. And so it works exactly like a lens then. This distance from the focus to the surface of the mirror is our focal length. And it's going to obey all of the same optical properties that we talked about with lenses. So let's see how this will change things and how we can, the big thing we want to know is, since we already know our lens equation still is going to hold. If I have a focal length, and that should be an I, if I have a focal length and the object distance, then I can figure out the image distance from that. So my goal here, my main goal here then is to get that focus. How do I find that focal length? So let's take a look at that then. Before we get into it though, one quick question. Now, a lens that's made out of glass, you can only make it so big. Glass, with especially heavy glass, will actually distort its shape over time. It's got this kind of plastic-like flow to it. So I can't make lenses arbitrarily big. Mirrors, on the other hand, though, it's just a silver piece of aluminum. I can take aluminum. You may think, well, I've got glass in my bathroom mirror, but that's really just to protect it. The glass isn't doing anything. So I can take just a piece of aluminum and then polish it really nice, and there's my mirror. Not only that, then I can build it very large because I can build supports around the mirror. So I can make this thing really huge. Why would I want to do that? How does the brightness of the image relate to the mirror's surface area? Think about conservation of energy. Well, as the surface area goes up, I'm gathering more of those rays. The energy in each one of these rays is the same. However, now I'm concentrating them all here. So if I have a larger surface area, you can think of that as capturing more of these light rays. So my energy is also going to go up. So they're going to be directly proportional. Make sure that makes sense to you. So this is why size matters. This is why the bigger the telescope, the easier it's going to be for you to observe what you want to do, because you can gather more energy with that. Okay, so we need to figure out how to get the focal length. So let's go back to some of our concepts that we talked about. So remember that we said that the radius of curvature is the radius if I had this entire sphere here. So even though I don't have the entire sphere, and so don't technically have a radius, I have a radius of curvature. And one way I like to think about that is, imagine I've got a string with a fixed length, and I put one at the center of this, where this lens is, and then I swing the string around, and it's going to paint right along. As I move that string, it's going to paint right along this. That point where I have to hold the string so that the other end stays exactly on the surface of that little piece of the sphere, that is called my center of curvature. And that's what we use with C right here. So this is not the focal point, and this is where students get confused a lot. This center of curvature here is where I would hold that string, like that, okay? And so then the radius of curvature is simply the distance from the center of the curvature to the surface of the lens. And so we've marked here the focus. This is the focus right here, because you saw that our rays are going through. Now we've drawn two of the principal rays here. This one's coming in parallel. Our rules still hold. If it comes in parallel to the center line, it's going to go through the focus. And so that gives us this. Here I have another one that's parallel to the center line. So it's also going through the focus, and that's how we can determine it. So the focal length is that distance dB right there. Okay. So any light ray that passes through the center of curvature, what's going to happen to it? And we're not quite at microtask 3 yet, but any light ray that passes anywhere through the center of curvature, what's going to happen to it? It's going to get reflected right back. Do you see that it's going to be exactly at the normal? No matter where I am, I'm going to be pointed directly at it. Because think about that string, right? That string is always going to be at a right angle to the surface of it. So any ray that passes through the center of curvature is going to get reflected right back out. Now, the light ray that passes through the center of curvature and the focus then, that's what we were talking about right here. It's going to go straight back like this. You see how that works? So keep that in mind. This is going to help us pin down how to get an expression for our focus in relation to our radius of curvature. All right. So let's get it set up. So here's how we're going to do it. And we're going to do this in what you might think to be kind of a convoluted way, kind of a backward way. I want to find DE, right? However, I don't have any right triangles here. A, D, and E are not going to form a right triangle. And we know that using right triangles allows us to use sine and cosine and tangent and makes our jobs a whole lot easier than doing some of the more complex laws of sines and things like that. So if I want f, I want to find it relative to r. Well, the distance from C to E, let's use a different color here. The distance from C to E is what? That's going to be our radius of curvature, r. Can you see that? So my focal length then is going to be the radius of curvature minus this distance right here that we're going to call CD. So not C times D, minus the length of that line, CD. So do you see that if I can find this, and you see I've got a number of right triangles that I could use to work with that, then I can get the focal length. So that's going to be our plan. That's going to be our approach to doing this. And the microtask walks you through it. If you want a challenge, pause the video and see if you can do it, because it literally takes you through each step. Okay, but let's take a look at it together here. Okay, so the first one says, what is the angle CAD? That's this angle right here. Maybe I should choose a different color. Let's switch to red. So this angle right there. What is that angle? And how do you know? So CAD. Well, this is some of the only physics actually in it. There's no geometric relationship between those two. But we know from the law of reflection that theta is the angle of incidence, and so that must also equal our angle of reflection. So this angle must be theta. So that angle is theta. All right, so then it says, make sure that makes sense to you, because we get sometimes we get stuck in the, oh, where's my geometry? Well, don't forget that this is a physics class too. So what is the angle ACD? That's this angle. And how do you know? Well, this is geometry. Well, these are alternate interior angles. So I've got parallel lines and a line that cuts through. So these two angles are also the same. So that must also be theta. Okay, make sure you're following each step so that we can kind of just walk through these triangles. And that's pretty typical. That's why we call it geometric optics, is because you're really just using the geometry to figure out what's going on. What is the angle ADB? Well, that's this angle. This might be a little trickier, but it's still geometry. So we know this angle is theta, right? Well, if it's a right triangle, then this must be 90 minus theta. You can see that? All right, so now it wants to know what is CDB. That's this angle. Well, we decided that this is theta, right? Well, I've got another right triangle here, so this must also be 90 minus theta. So that's interesting right there. That immediately tells us that this angle and this angle must be the same. Do you see that? They're both 90 minus theta. Well, if they're both the same, then what can you say about the lengths C to B and B to A? And why? Well, so I have all three angles are the same. I have all three angles are the same. And so based on that, then I know that they must be identical triangles from this, or at least they're got to at least be similar triangles. But you can see that because they share a side, let's make sure we're clear on that. If all three angles in the two triangles are the same, they are similar. They still might vary by a scaling factor. But in this case, they share this side BD. Since BD is the same in both of them, the scaling factor is just 1. So they're identical triangles. So these triangles are absolutely identical. And so if that's true, then CB must be equal to AB. So this point B just defines the midpoint of that line. All right? Okay, so AC is the radius of curvature. Make sure that you see why. That's that string we were talking about. So what does CB equal in terms of the radius of curvature? CB is simply going to be 1/2 R, because we decided it was the midpoint. So we now know the length of CB in relation to r. And we know the angle BCD, that's this angle, remember, which one was it? BCD was theta. You can go through your little list here to look that back up. So I want an equation that will give CD, because remember that was our goal. If I could find CD, R minus CD will give me F. So that's my goal, is I want to find that CD. So, well, now I've got a right triangle. I want the CD as the hypotenuse of that right triangle. So I've got an angle here, and I've got the length of this side here, this CB side. I know that this is 1/2 R. What trig function is going to give you CD? So take a look at the triangle then, and let's see what we can find. So here's my right triangle. CD is the hypotenuse, and this is my adjacent side from this angle theta. So that trig function then, of course, is going to be cosine. So cosine theta is going to equal my adjacent, which is 1/2 R, divided by the hypotenuse, which is what we're looking for, CD. So now all we need to do is just solve this for CD. So I'm going to move my CD to the other side. So I'll move my CD over here, and my cosine theta goes down. And I get CD equals 1/2 R over cosine theta. I'm going to clean that up just a little bit. We'll say that CD is equal to R over 2 cosine theta. Over 2 cosine theta. And that was our goal. Remember that if we can find CD, R minus CD is going to equal F. Okay, so let's take that and let's find that expression. And we'll switch back to black for now. Okay, so we know that F is equal to R minus CD, and F is equal to, therefore, R minus R over 2 cosine theta. So now I can factor out that R, and I get F is R times 1 minus 1 over 2 cosine theta. So there's the equivalent that would allow me to use the radius of curvature and figure out what is going to be the focal length. But we've got a bit of a problem here that maybe you didn't notice. Let me clean up my cosine here just a little bit so we can read that. The focal length depends not only on the radius of curvature, but also on the angle at which the light is coming in. So if this is my sphere, this is my mirror, if I've got light coming in at some angle here, it's going to reflect at a different focal length than I would have, at a different focal point than I would have gotten if I had one coming at a slightly different angle into there. Well, that's a problem, because that means we're going to get some distortion in our image. It's just going to be a little fuzzy. And so this effect is called spherical aberration, and all spherical mirrors have this problem. For the curious, most astronomical mirrors are actually parabolas, so that no matter which direction it hits, it's always going to get reflected at the correct angle from that. But if my mirror is small, so as long as I don't have just one of these massive, massive mirrors, if my mirror is small, then that angle that it's coming in will always be small. So theta will always be much less than 1. So I can use my small angle approximation. And so for cosine, the small angle approximation is approximately 1. And you can test that on your calculator. Take any small number, 0.0001, something like that, hit cosine on your calculator, and you're going to see that you get exactly the same number. So the small angle approximation will hold in many, many cases. So let's use the small angle approximation to simplify what we have here. So if cosine theta is approximately 1, then I have R 1 minus 1 over 2 times 1, which is just R times 1 minus a half. And so we're finally left with our final equation, which is actually very, very simple. The focal length of the mirror is always going to be half the radius of curvature. And so this is called the mirror maker's equation. Remember our assumptions, though. We're assuming that theta is very small. But for a spherical mirror of kinds that you're going to use in everyday life, it's a pretty good approximation. So it's going to hold. So that one's worth keeping in your flipbook. Now, as we said, once I have the focal length, everything obeys the same lens equation that we've been using before. So let's take one of these spherical mirrors and let's apply the lens equation to that now that we know the focal length for it. So we're going to go ahead and delete this one. We'll delete the one over here. All right, so take a look at the scenario. So suppose we have an object placed 80 centimeters in front of a spherical mirror that has a radius of curvature of 0.5 meters. Okay, and as we said, we're going to assume it's small enough we can use a small angle approximation. How far away does the image appear? And so remember, in physics speak, that means I want the image distance. And then it wants to know what is the magnification and how tall does it appear. All right, so this is how we're going to get going then. So for my scenario, we need to find the image distance, m, and the image height. Those are the three things that we're looking for. So it says, how far away does the image appear? That's going to be I. What's the magnification? Okay, that one's easy. And how tall does it appear? Well, that means we must be talking about the image. So it's really kind of important that you go through these symbols to make sure that you're answering what the question is actually asking with this. Okay, so we know the radius of curvature is 0.5 meters. So we're going to use the radius of curvature to get F. And then we're going to use our object distance D with F to get I. Now the next part says we need the magnification, but we have an equation for the magnification. So we will use the magnification equation using I and D. Well, once I have that magnification, then I can use the magnification equation using the object height and the image height. So that's our plan. And it's always a good idea to have this plan laid out. It'll really help you when you're trying to organize this. So we're going to use R to get the focal length. Once we've got that, we can use the lens equation to get the image distance. If I have the object distance and the image distance, I've got the magnification. Once I have the magnification, then I can get all of the other properties. So I can, for example, if I have the object height, I can get the image height. All right, so let's define our symbols here to make sure that we're all on the same page with this. There's my tablet where I can write. Okay, so the radius of curvature we said was 0.50 meters. We said that the object distance was going to be 0.80 meters. We said that the object height, which we call HO, is going to be, what did we say, 50 millimeters. So that's going to be 0.050 meters. And double check that you've got your conversions correct. So it's 80 centimeters. The object is half a meter. The radius of curvature is half a meter, and then the object is 50 millimeters tall. And remember, you can always write that using our suffixes, our engineering suffixes. So R was already in meters. If I have 80 centimeters, that is 80 times 10 to the minus 2 meters. If I have 50 millimeters, that's 50 times 10 to the minus 3 meters. And that will always work for you. Okay. Now, things we're looking for then, we need to know the image size in meters. We need to know the magnification, which has no units. And then we need to know the image height. Now, we already know that we're going to need to find the focal length. But for now, these are the symbols that we know we need. And it's a good strategy to just not add any more symbols until you're sure that you're absolutely going to need them. Okay, so we'll put that to the side here for just a minute. All right then. So what equations are we going to use? Well, we already said that we're going to use the mirror maker's equation. So, but let's start off by thinking about, okay, I want to use the lens equation. 1 over F is 1 over D minus, or plus, sorry, 1 over I. Because writing this equation down tells me I need to find the focus. I need to find the focal length. So if you thought ahead and you're like, oh yeah, of course I need the focus for that, great. But if not, writing this equation saying, okay, I want I I is my goal, and this is an equation that will give me I, then the problem's telling you, oh, okay, I'm going to go, I have D, so all I need to do is get F. So we're going to add F to our symbol list here. So F is the focal length, and we don't know what that is. So now we know we need to have 4 equations to make this work. All right, so let's put all this together then. So we've got our first equation. We know that's going to be the lens equation. Now we need an equation to get F. Well, we just derived that. That's going to be our mirror maker's equation. So we also know that F is going to equal to simply R over 2. So that's 2 equations. I need 2 more, and our plan has already told us what those are going to be. We're going to need the magnification equation. So remember, there are 2 forms. So we're going to need, the first one, we're going to need the one that involves the image distance and the object distance. And remember, that one has a negative sign in front of it. And then the other one that we're going to use is we're going to use HI over HO, the image height over there. So now we've got 1, 2, 3, 4 equations, 4 unknowns. The problem solved. All we need to do is just put it together and do the math. All right, so it's usually a good idea to start with the equation that's going to give you what you want. So we're going to start with this lens equation, which is now also our mirror equation. So that's 1 over D plus 1 over I. I need F, so I'm going to put that in here. 1 over F is going to be 2 over R. Make sure you see what I've done there. 1 over D plus 1 over I. All right, so now we want I, so I'm going to have to move this to the other side. And so that's going to give me 2 over R minus 1 over D is going to equal 1 over I. I can't just flip these. Lots of students want to just flip all 3 fractions, and that's not going to work. We have to get a common denominator first. Well, our common denominator here is going to be RD. So that tells me that 2D over RD, see that the D's cancel and left with 2 over R, minus 1 over RD, lowercase d, must equal 1 over I. And so putting those together then, I get 2D minus 1. Oh, whoops, sorry, that should be R, right? Because we need the R's to cancel and be left with 1 over D. Let's redraw that. And so then this becomes RD. There we go. Divided by RD must equal 1 over I. Now we're going to flip both sides. And so I have my final expression here for this. I is equal to R over D times 2D minus R. And I already know what those are. And so if you take your values and you put them in, punch them into your calculator, and I get an image distance of approximately 0.364 meters from that. So make sure that you're getting the same thing. All right, now we've got everything that we need. Our magnification, our first form, so we've used this one, we've used this one. So our first form says we're going to use minus I over D. And so in that case, that's just going to be the 0.364 meters divided by our object distance, which we go back over to our symbol list, that was 0.8 meters. And so that's 0.80 meters. And when I did that, and of course there's that minus sign in front of it, when I did that, I got negative 0.454. So how does the image appear? Is it upright or is it inverted? It's inverted. So the image that you're going to see in a mirror, in a spherical mirror, is also going to be inverted. So the mirror is behaving exactly like the lens. And this is true with an astronomical telescope. Even if I'm using mirrors, everything is going to be inverted and reversed. All right, then the last thing we need is we want to have that object height or the image height. Well, so we've used this one now. So our last one then is going to be HI over HO. And we're going to solve that for HI. And that very simply gives us M times HO. Well, we found our magnification, and we know that our object height was given over here. That was 0.50 meters. So when I multiply those out, then I'm going to get 22.7 millimeters. And because this is actually going to be, since M is negative, then my image height is actually negative 22.6 millimeters, which means it's inverted. So remember, if my image height is negative, my object height is this way, then my image height is this way, then it's inverted. But that makes sense because that also matches our magnification there. But when you're putting in your answers in for your homework, be very careful to make sure that you've got the correct sign with that. So this kind of mirror that we've been looking at is a concave mirror. And we talked about concave lenses and convex lenses, and they work basically the same way. Remember that if this is my light coming in, well, that's a concave mirror. On the other hand, if my mirror looks like this, then that's a convex mirror. And you have seen these before. These are like the mirrors that you have on the right side of your car. Often they'll say, caution, objects are closer than they appear in the mirror. That's because you've got that convex mirror there. These are also used for security mirrors. If you've ever seen the big mirrors they'll have up on the ceiling. So they'll be convex so that they can see a wider field of view. Okay, so here we're looking at the last microtask. Let's zoom in on that just a little bit. And let's get rid of our equation from our last work there. There we go. Okay, so now I've got a mirror. Now remember, this is not a lens, it's a mirror. So we've got two of the three principal rays drawn. So one is parallel to the mirror axis, that's this one here, and the other goes straight through the center of curvature, not the focus, which is back here. So we want to know what is the orientation of the image, and we're going to do the same kind of ray tracing that we did before, but remember, things are bouncing off of the mirror now. So remember that if it hits the center of curve, if it comes straight into the center of curvature, it's going to get, let's use red, it's going to get reflected straight back along its path. And if it's parallel here, then it's going to get reflected away from the focus. Would have been through the focus with the convex mirror. Put that right about there. Now, obviously, it doesn't look like these rays intersect. So just like we've done before, maybe we can do a little bit better on that one by making it go through the focus. Line it up like that because we need to trace it back so it goes through the focus. And this one goes through the center of curvature. So there is my image right there where it forms. So what is the orientation of the image? Well, it's upright. And does it appear larger or smaller? Well, it's going to be considerably smaller. And this is why you would want to use this as a security mirror, because now since I've got everything is smaller, I can fit a wider field of view in that one mirror. And so I can see the entire store just from that one mirror. This is also why the little side view mirror says objects are closer than they appear, because they're smaller. They look smaller than they would just with a flat mirror. And even though that side view mirror looks like it's flat, it's actually not. So your brain says, oh, there's something small. It must be a long way away. But in fact, it's being reduced in size because of the fact that it is this convex mirror with that. So now we've talked about the two main types of optical systems. We've talked about lenses, which remember are primarily made out of glass, but they could be made out of water or any other kind of substance that allows the light to pass through. And then we've talked about mirrors, which is anything that's going to reflect that light back. Aluminum, could be iron, could be anything. So we talked about how we can form images with those, and often we can make it so that the image is going to be brighter than it would have been before because we're gathering a whole bunch of these light rays, each one of which has the same energy, and we're concentrating that energy into a point. One of the more famous applications of this type of optical system is telescopes. And so that's what we're going to talk about next time. And it's basically just going to apply what we've been talking about here. So make sure that you really understand the concepts from these last three lectures, and then we'll get to do something cool with them when we start talking about telescopes. We'll see you next time.